welcome to the Temporal Graph Reading Group today, everyone. Yeah, so for today's talk, we are glad to host Rishabh Ranjan from Stanford University, who will be presenting their recent work at NeurIPS 2024 Datasets and Benchmark Track on RELBENCH, a benchmark for deep learning on relational databases. So Rishabh is a second-year PhD student at Stanford University. He is advised by Prof. Yuri Leskovec and also works with Prof. Carlos Gerstrin. He completed his undergrad in computer science and engineering at IIT Delhi, where he was the president's gold medalist for the class of 2022, and also received the award for the best undergrad thesis in CS. And prior to PhD, he spent a year at CMU as a visiting researcher. And his interests lie at the intersection of relational deep learning and foundation models, with the research goal of extending the success of foundation models like LLM to structured data such as tables, time series, and relational databases. Yeah, and I will hand the mic to you.
Okay. Thanks for the introduction, Andy. Nice to meet you all. I'm Rishabh, and so in this talk, I actually wanted to cover two papers. So this is the paper that Andy introduced, which is RELBENCH, a benchmark for deep learning on relational databases. This got accepted at NeurIPS 2024 Datasets and Benchmark track. But to understand this paper, I should also discuss an earlier paper which got accepted into the ICML 2024 position paper track. And that paper was titled Relational Deep Learning, Graph Representation Learning on Relational Databases. And so apologies for the slides. So I'm reusing slides from our recent presentation on at the Stanford Graph Learning Workshop, and these are pretty polished slides, so I thought they would be a good fit for here as well. And this particular set of slides is from Josh. The next set of slides is from me. So the way I want to structure this talk is I can spend maybe about 20 minutes on the first part, which is relational deep learning, and then 20 minutes on the second part, which is RELBENCH, and then we can have the rest of the time for questions and discussions. And also, I want to maybe keep it a little free form, so feel free to interrupt, ask questions, interact, and so on. So to start off with, relational deep learning, graph representation learning on relational databases. So here, I'm going to provide the deep learning blueprint. And in the next talk, I'll provide benchmarking, empirical validation, and research infrastructure. So relational databases are a major global data source. They come from domains such as commercial activity, such as in e-commerce domains, social networks, electronic health records, and you have the structure of multiple tables which are connected by foreign keys and primary keys. So for example, in the social network schema, you have users, you have user settings, external accounts, following relationships, and so on. And then maybe external accounts has a user ID foreign key, which points back to user ID in the users table. And same with the other schemas on this slide. And most of the world's important, valuable data is actually stored in relational databases of this kind. So this slide shows that relational databases are like 166 systems out of how many systems in total that these guys considered from dbengines.com. And that is more than 1/3 easily of this pie chart. And what you want to do with these relational databases is to make predictions. And such kinds of predictions are routinely made by companies, banks, hospitals, and so on. So here's an example. Here are some examples of the kinds of predictions that you would like to make on e-commerce data. Will a customer churn? That is, will a customer stop using your service? What will be the lifetime value of the customer? What is a product that you can recommend to a customer? Is there fraud going on in like some transactions between some users and so on? Then here are some example tasks for electronic health records. Will patient return to the hospital if discharged? Who is the patient who has the greatest risk to life in next 24 hours? And as you can imagine, making accurate predictions on these kinds of tasks can be very critical. And maybe another thing I want to note is that all these tasks I have mentioned here are temporal tasks because you're trying to make a prediction on the future at the present. And maybe I'll speak to that more later, but just wanted to point it out. So, what is the current state of the art of machine learning on relational databases? And what's the problem with that? The problem is that it is slow and manual. So, currently, what you would want to do is first convert this into a table because there does not exist a machine learning method which can directly take a relational schema of tables and work on that. And you do that by engineering features manually. So, for example, a human would have to decide that maybe this is a useful feature to have, number of purchases on Mondays, or time since last purchase, price of the most common purchase. And then you write SQL queries to compute these features from your underlying database, and then convert this entire thing to a tabular machine learning problem. And then you solve it with some tabular machine learning method like XGBoost, which is still very popular in industry. And then you iterate because maybe the features were not useful, maybe you come up with better features and so on. But other fields in deep learning moved to end-to-end learning a long time ago. Like this situation is very similar to what used to happen in computer vision 10 years ago, where you would first have a feature detector like SIFT features or hog features, and then you would have a simple SVM classifier on top. But the neural network solution is to say you take the raw data at the input and just end-to-end predict the target that you want to predict. And this is what we are trying to strive to do for databases in this paper. The question is, how can we do end-to-end deep learning on databases without any manual processing? And the key insight is that this can be done. And this can be done because relational databases can be modeled as temporal heterogeneous graphs. So every table denotes one node type, and then every row in that table becomes a node of that type. And then you can link two nodes if the foreign key ID of one node matches the primary key ID of the other node, right? And then the column features for the table in this model becomes the node features associated with the heterogeneous graph. And the key thing to note here is that this is an invertible transform. This is a lossless conversion. The graph is not approximating any part of the relational database. It is representing it as faithfully as possible. So we're still modeling the raw database rather than some features extracted from the raw database. And now the prediction problems that we were interested in solving become graph machine learning problems. So there are node level tasks, such as predict the churn of a user or predict the lifetime value of a user. Note that the user is a node here. Then there are link level tasks, such as product affinity, because you want to predict it for a pair of users and product. Similarly, recommendation for every user recommend products. And then there are graph level tasks, which can be defined across multiple nodes and multiple edges. Something like fraud detection is this subgraph suspicious activity. And we can use GNNs to solve this graph machine learning problem. I mean, we are all familiar with GNNs, I guess, so I'm going to skip these slides. And I'll jump directly to what the overall pipeline then looks like. We had a relational database. We converted it to a graph machine learning problem. Then we use a GNN architecture to we train a GNN architecture on that. And then we use the predictions of the GNN as solutions to our problem. Now, how is a task defined in such cases? The really appealing property of relational databases is that you can recover ground truths from the historical data. So for example, if you have a task such as how much will each customer buy in the next 90 days? Now you need training labels to train a machine learning model on this task. But because you have historical data, you can gather training labels from the past. So you can shift the current day to 90 days in the past, maybe 180 days in the past, 270 days in the past, and see that from that point to the next 90 days, how much did each customer buy? And that becomes your prediction target. So this is the phase we refer to as a training table generation. And then a training table looks like this. It has a customer ID specifying which node you want to predict on. It has a 90-day target, which is the prediction target or the supervision label. And then there's a seed time, which tells you that at this time, if I look at the database, what is the prediction going to be? And then we can link this to just as any other table in the set of relational tables that we have. So now I want to jump to the advantages that this kind of blueprint of relational deep learning brings for us, or in general. The GNN can learn to aggregate information across nodes. And so it can learn cross-table features in an end-to-end manner versus for the traditional approach, the only way to incorporate cross-table features is to do handcrafted feature engineering. And the reason we expect GNNs to be better than handcrafted feature engineering is because GNN can catch complex signal that is hard for a human being who is manually engineering features to identify. So for example, there might be interaction between the users and the products table when you're trying to think of which user has bought which product. But there's also interaction between users and views table. And the interaction could be like, how active was the user in the past? And considering all these interactions, for a human, it becomes bottlenecked by like the creativity of the human or just the cognition of the human. And the other advantage is that it naturally supports point-in-time prediction. So what we mean by this is that if you want to predict at a particular time t, you can mask out all the future nodes and only see the past nodes. And you can ensure that your model does not have time leakage, that your model was only trained to predict the future given the past. And this is a common source of time leakage bugs in industry today, where you write a SQL query that introduces a time leakage, and then you train your model on information from the future. And this model performs very well in training, but it performs very badly in deployment because the information from the future is no longer available. And so to summarize what deep learning on relational databases with this blueprint of relational deep learning gives us is more accurate models that are end-to-end learnable, multi-hop reasoning to identify complex features, much less manual work because you're not manually generating features or writing SQL queries to get those features or doing ETL to extract those features from the data. And it's a simpler deployment because similar to the last slide on point-in-time computation, we don't have to recompute the features every time things get updated. You just have the same model and introduce more nodes in the graph, and the GNN can handle it. You don't have to worry about features, storage, time leakage bugs, etc. And So this, what I presented so far is based on our ICML 2024 paper, which is Relational Deep Learning, Graph Representation Learning on Relational Databases. Please check it out. And this is the end of this part of the talk. So maybe I can pause a little bit here and see if people have questions, comments before moving on to the benchmark part of the talk.
Um, yeah, so thanks for the discussion on the paper. Um, so just so like the idea sounds great, and I have worked with it before. So one question that I had, so I don't know if you thought about it before, is how do we build a foundation model on top of potentially multiple tables? So here it talk about you train a model from scratch end to end for a single relational database. But is it possible to, let's say they have very similar schema, like with slight variation on the attributes and so on. And then is it possible to train a foundation model that can do similar task and leverage the different data from all these different um, like relational databases to get better performance, to achieve some level of transferability?
Yeah, thanks for the question. It's a very good question, and that is basically the question I've been working on in my current research. And I mean, it makes sense. This entire work opens this exciting opportunity to do transfer learning from many databases, or even within the same database that you can define so many tasks, and then can you do anything better than training separate models for each new task or each new database? And then the setup you described is maybe a slightly simplified setting where you are saying that, okay, maybe the schema is shared, or maybe the schema
Yeah,
is slightly similar. But in my current project, for example, we are trying to tackle the even harder setting where the schema itself can change, and that allows you to train on databases and tables of very different schemas and then apply it to very different schemas. And I'll tell you the main challenge, or the main thing that needs to change from this kind of approach that I'm presenting today. So in our current model, we have tabular encoders that learn how to encode the columns of a table into node features.
right,
And these tabular encoders are trained on the data set itself, so they can only encode. So they are initialized for a fixed schema, and then they're trained to only work for like the data that is seen in that table. And then they do
right.
a good job because they
Yeah,
can do this. But what a foundation model would need is that you give the schema information to the model itself. Or so, for example, you should be able to provide like the column name and the column value, and the model should be able to work irrespective of what the column names is. Or maybe like the harder problem is not the column name, it's like the number of columns, for example. You
right.
need to you need a model that can support any number of columns and so on. And one naive approach, for example, is to use text as a natural interface, because LLMs have like the word knowledge to understand maybe what the column name means, and then you can maybe get an embedding that makes sense.
Right.
Uh, or just try to put the schema in the context of the model, like of an LLM, or a GNN, or a GNN LLM hybrid in some way, so that the model can adapt via in-context learning to the current schema.
Right.
But these are just ideas that I've been exploring, and I would be interested in hearing other people's thoughts as well on what can be done here.
So we see this year there's a lot of recent work on graph foundation models. So I
Mhm.
think as your talk like mentioned, so basically a lot of the times the representation boils down to at some point like that would become a graph. So the main technical challenge is first of all how to deal with the graph structural differences as well as the tabular side, as you mentioned. So
Mhm.
some of the techniques that people use is some sort of dimension reduction techniques where no matter what the input dimensions are, you want to reshape it to some fixed dimension that the model can keep as constant across data sets. So
Mhm.
like using SVD or something like that. But that also come with the downside of you having to do these computations and pre-computations and so on. Um,
Mhm.
so I think there's still a trade-off, but but I like your like NLP approach to this as well. Um, but it might be expensive if you would need to, constantly doing this kind of like check with the with the language model as well as how to like understand like what the field will be and how to best embed it. So I think there's a lot of technical challenge here, but I think this can be a very interesting work. So happy to discuss more offline or see when your paper come out, and then maybe you can present again at the reading group for more
Yeah,
discussion.
yeah, I would love that, but this is also a very recent project, so it'll be some time before a
I see,
paper
I see.
comes out of this.
Okay.
Um,
Yeah, yeah. So happy to discuss more offline. So I thought about this a little bit before as well. So
mhm,
yeah,
mhm. Yeah,
sounds good.
I would love to discuss. Yeah.
Yeah. Okay. Sounds good.
Um,
Please continue the talk. Yeah.
okay. So if there are no other questions or comments, I can move on to the second part of the talk.
Just sorry, before you move
Yeah,
on,
yeah.
there is a question in the question and answer box. If you can see, or I can.
I don't know where should I see this?
Maybe you can't. I will read the question. It says,
Okay.
thanks for
Uh,
the presentation. I have a question. There is a training table. What about the validation and test tables? How this part works?
Okay. Let me go to this. So, maybe a training table is a slightly misleading name. Maybe we can call it a task table because the validation and test table would be very similar to the training table. The only difference is that we are using temporal splitting. So the seed time for the training table will always be less than the validation seed time. Then the seed time for the validation table will be between the validation seed time and the test seed time. And the seed times for the test table will always be greater than the test seed times. And another thing I would like to highlight here is that the database remains the same across the training, validation, and task tables. So the splitting happens only for the task tables, not the database tables. But also, we need to make sure that we are temporally consistent. So when you are trying to predict for a particular seed time, you should only, like the machine learning algorithm that you design, should only see those rows in the database which have a timestamp of less than equal to seed time. I hope that answers the question. Okay. So yeah, now I come to the next part of the talk, which is RELBENCH, a benchmark for deep learning on relational databases. Our website is relbench.stanford.edu, and our GitHub is snapstanford/relbench. And we have 200 plus stars on the GitHub already. So I very much encourage people to go and check out our GitHub and our website. So the last talk was the relational deep learning blueprint. This talk will be about validating that this blueprint actually works with real benchmarks, real baselines, real data sets. And in doing so, we also have set up a research infrastructure to do research on relational deep learning. So that's what this talk is going to be about. So first of all, there's RELBench, which is the benchmark and the Python package. But the thing I want to emphasize about RELBench is that it is a framework to enable research on relational deep learning. It is more than just a collection of databases because this entire field is so new. So it provides data loading, it provides task specification, graph construction, model building. And for model building, we have tight integration with other libraries such as PyTorch Geometric for GNNs and PyTorch Frame for tabular modeling. And then we have standardized splitting, standardized metrics, and finally a leaderboard to track progress. We have an easy to use Python package. So you can pip install RELBENCH, and then RELBENCH provides classes for objects like table, database, dataset, task, and it provides easy ways to just download a particular data set, get the database, download a task for that database, and then get the standardized train, val, and test tables. And finally, once you have trained your model and have predictions, it provides a standardized way to evaluate your test predictions. We have 7 diverse datasets from 4 different domains. We have Rel Amazon, Rel Avito, Rel HM from e-commerce. So Amazon is the Amazon products dataset. Avito is an event recommendation dataset. HM is H&M fashion dataset from Kaggle. Avito is also from Kaggle, by the way. We have some social network datasets such as Rel Event, Rel Stack. Rel Stack is Stack Exchange. Then we have sports datasets, Rel F1. So it has information about F1 races spanning 55 years. And it is a very comprehensive dataset. You can find everything that has happened in F1 in there. And then despite that, it's still very small. So it's a very, very interesting dataset to try out initial ideas on because it's so small that you can run the iteration loop very fast. And then there's the medical domain for which we have clinical trials dataset in Rel Trial. Our datasets have rich schemas. So we have 3 to 15 tables, 74,000 to 41 million rows in a database, 15 to 140 columns in a database, and the time spans from 2 weeks to 55 years. And 55 years, like I was saying, is from the Rel F1 dataset. And just to give a sense of the kind of schemas that we have, I have put 2 schemas in this slide. One is Rel Amazon, which is a simpler schema with just 3 tables, customer, product, review, and you have things like review text, summary, rating, verified, customer name, title, description of the product, and so on. And then on the other extreme of expressive schemas, you have Rel Trial, which is a clinical trials database, and you have tables for studies, outcomes, designs, eligibilities, sponsors, facilities, and so on. And you can see that there's a lot of columns in some tables. So there's rich feature information for entities in this table. Then we have a total of 30 real-world predictive tasks on them. There are 3 kinds of tasks. One is entity classification. So for example, predicting the churn of the user or the churn of an item for Amazon, predicting the badge of a user on Stack Exchange, predicting the outcome of a study for clinical trials, and so on. Then the second is regression tasks at the entity level. So predicting the lifetime value of the user or the lifetime value of the item on Amazon, predicting the click-through rate of the ad on Avito, and then predicting the position that the driver got in a race for Rel F1. And then finally, we have recommendation tasks. So predicting the item that a user will purchase on Amazon, predicting the ad that a user will visit on Avito, and predicting the posts on which user will comment for Stack Exchange, or posts that are that can be suggested as related posts on Stack Exchange. And finally, although we have these 7 data sets and 30 predictive tasks out of the box, the RELBENCH framework is extensible, and it is easily possible to use your own data in RELBENCH and to define your own ML tasks. And we also have detailed tutorials to do that. And once you put your data in this format, which is, by the way, not a lot of work, you can also run R scripts directly on your data set. So what this allows you to do is run our RDL implementation on your database and task and see how well the GNN does under the current modeling. And then if you do that, I would encourage you to also contribute your data to RELBENCH. So again, we have contributing guidelines, which are detailed instructions that you can follow to just open a PR on GitHub. And if everything looks good, we are happy to incorporate your data in RELBENCH. And maybe another thing I would like to point out is an exciting thing that recently happened is someone else had a data set of 80 databases, and it was in a different format, but they're writing an integration, a small integration library so that those databases can also be loaded into RELBench. And the reason I bring this up and the reason I'm personally excited about that is because, so for example, Andy asked this question on foundation model. And one challenge for foundation models on relational databases is the data problem, because you need a lot of diverse data to train a foundation model or like to train at the scale of a foundation model. And being able to just get access to 80 high quality databases in RELBench, I think would be super exciting. And this is why I'm also interested in trying to incorporate as much data as possible into RELBench, which is why we have a lot of support for adding new data sets. So now I want to move on to the benchmarking part of the talk. So there will be two sections here. One is to compare RDL versus single table baselines, and then later we will see how RDL does against manual feature engineering. So single table baselines first. So entity classification, the metric is a area under ROC curve. And here the baseline is just like GBM, but on a single table. And we see that RDL outperforms like GBM almost everywhere, except maybe here, but it's like a very small difference. And then on average, RDL is 20% better than like GBM. Then we have entity regression. Here the metric is mean average error. And here again, we see that RDL outperforms the light GBM baseline on almost everything, except maybe a few minor losses here and there. And here we also compared with a set of non-neural or non-machine learning baselines, simple baselines like what if you predict zero globally, or what if you take the mean of everything and predict that, or what if you take the mean but only for that entity and predict that. And the reason these columns are important is because these columns helped us select our tasks such that the tasks have the right amount of predictive difficulty. So our tasks in RELBench are like not so easy that even a global zero baseline does well or a global mean baseline does well. And then the overall picture is that RDL is 8% better than the previous baseline of like GBM. And finally, for recommendation, we have mean average precision as the metric. And here we have two instantiations of our RDL. One is with GraphSage and the other is with IDGNN. And this is a very interesting thing we found in these tasks is that for some tasks, GraphSage wins and the other IDGNN wins. And it seems to have something to do with the task characteristics. And we have discussion for this in the paper too, is that because if you notice, whenever GraphSage wins, the global popularity baseline wins over the past visit. So 31 versus 7, 24 versus 6, 18 versus 5, 11 versus 4. But whenever IDGNN wins, the past visit baseline becomes more important. So 3.66 versus 0.01, 1.95, 0.00. And this you can see everywhere, like 15.9 versus 4.9 or 17.3 versus 3.75. So what we think is happening is that for tasks where the past visit gives you more informative signal, IDGNN is able to capture that well. But for tasks where the global popularity of a product, let's say, is a more predictive signal of what to recommend, then the graph stage version captures that well. And I think this also points to an interesting research project where you try to come up with an architecture that can do well in both of these settings, and that can just learn what is the right kind of predictive signal to extract from the graph. And so here again, the summary is that we are better, but unlike the previous two slides, here we are a lot better than the previous baselines, which is around 300% better on average. And in some of these cases, like more than that, it's like 476% or 550%. So that's a lot of gain. So the
Just
takeaway,
to,
yeah.
yeah, sorry to interrupt. Just to mention that the recommendation task here is, from my understanding, is essentially just link prediction. Like it's very similar to link prediction on standard GNN learning, right? So,
Yes, yes.
so yeah,
I think
but
we,
the task definition itself, it's more like predicting if the user will interact with something, right? At a future time. So it's like temporal link prediction, basically. And we know that I would say the significantly better performance gain is also not surprising because we know that a lot of the GNN literature is focusing on doing link prediction tasks. I mean, from the temporal graph side, like almost all papers does link prediction. A select few does some no-level task. And we know that the architectures have been benchmarked on link prediction. So there's a lot more progress and innovation in terms of getting better link prediction performance. So it also makes sense to see that GNNs can do so much better in kind of link prediction here, in terms of the raw performance gain when compared to the other two tasks. But it also shows that we should have more architectures that work better with more like regression task or like no level tasks and so on.
Mhm. Yeah, thanks. That's an interesting point. And yeah, I think we have a very similar setup for this task as the TGB link prediction tasks. Yeah.
Thanks.
So yeah, the takeaway from these past few slides is that there is important predictive signal in the linked tables. And so if you just use the single table to make your predictions, such as in like GBM, then you're missing out on a lot of predictive signal. And that is why relational modeling is important. So now we move on to the, in my opinion, even more interesting part of the benchmarking, which is against manual feature engineering. So we did a user study with an expert data scientist, which is the prior gold standard for machine learning on databases. We recruited an experienced data scientist, Alejandro. I mean, he was here when I was giving the talk at Stanford graph learning workshop, but never mind. He has 5 years industry experience specializing in financial databases, and he was responsible for the full model building cycle of our user study. And in these slides, I want to give a sense of what the model building cycle looks like from a data scientist perspective. So for example, the task is, will a user be active in the next 6 months? And the first phase is exploratory data analysis, which is around 4 hours of manual work. And this includes plotting various things such as new posts versus year or frequency versus number of comments, and then making observations such as activity is seasonal. So you see, so these are like from the Stack Exchange dataset. And if you see, there's this interesting pattern where the activity dips. And Alejandro told me that these dips correspond to summer vacations. So people stop doing their homeworks during summer vacation and the activity drops on Stack Exchange. Then there are other observations, such as the number of comments follows a power law, or like that most votes are positive and only few votes are negative. And this kind of exploratory data analysis then leads to the second part, which is feature ideation. And you come up with features like, what is the number of weeks since last comment, or what is the score of the badge of a user? Is the location field filled out or not? And just coming up with features can take around 30 minutes. And the next part is the heavy lifting part, where you write SQL queries to extract these features from your database. So for example, these three features become hundreds of lines of code when you write it down in SQL. And then you extract those features with a SQL query and try to train an XGBoost on that. But obviously, you cannot just go in with the default set of hyperparameters and expect that to work. So you do a hyperparameter sweep, and that can take you 2 hours. And finally, you want to do a feature analysis and see whether the features you came up with were important or not. And sorry that this figure is very small, but you see this figure shows the features and the corresponding SHAP values, and only the top like 40% of the features are important, and the other features that the human came up with all that manual effort and labor to write the SQL queries, turns out to not be predictive at all. And you can say that maybe that was a waste of time and so on. But then usually there's an iteration after this, where you see all these SAP values and you try to come up with another set of features which are more predictive overall. So the upshot of all this is that you end up with a lot of features, manual features, like 54 in our case. This took 12 hours of high quality expert work, around 700 lines of code. RDL does not need any of this. The GNN can just learn everything end to end, no high quality manual work, no writing SQL queries to extract features. And yet, RDL matches or outperforms the manual features in most tasks. So in 11 out of the 15 tasks that we ran the user study on. And it reduces the human hours by 96% on average. So from 12 hours that you would need to do manual feature engineering to just around 30 minutes that you need to run the RDL scripts on a new task. And it also reduces the new lines of code by about 94% on average. So for every new task, you just need to write some code to express the task in a common format, and then the RDL script can just work on that task directly. You don't have to write any more specialized code for the new task. So then the takeaway from these last few slides is that RDL gives you better predictive features, but with much less manual effort. And so this is the paper that we'll be presenting at NeurIPS in a few weeks. The paper is called RELBENCH, a benchmark for deep learning on relational databases. Please check it out. And that is the end of my talk. Again, our website is relbench.stanford.edu. Our GitHub is napstanford./relbench. Here's the team. So it was a large collaborative effort, wouldn't have been possible without all these people. And finally, I would also like to use this opportunity to call out for contributions on RELBench, because RELBench, we aim to keep improving RELBench, and so there's a lot of scope for contributing, and we appreciate any contributions, be it data sets, tasks, maybe bug reports, new metrics, whatever. Thanks.
Thanks for the presentation. So if you have any questions, feel free to type in the chat or just unmute yourself. I think there's one question from the chat. It says, how scalable is RDL?
Uh, can you maybe be a little more specific? I'm trying to see how to interpret this question. So scalable. So if you're asking how hard it is to run the GNN scripts, one thing is that our benchmark is aimed at an academic audience. So I had these numbers are actually pretty tiny for industrial databases. Like industrial databases would have hundreds of tables and thousands of rows and thousands of, not thousands, like billions of rows and thousands of columns and so on, right? But we aimed RELBENCH at the academic audience. So our main goal was that it should be possible to work with RELBENCH. So all of these data sets are small enough that you can train GNN models on a single consumer GPUs with around like 30 to 40 gigs of memory should be plenty. And the training, so for the small data sets such as rel F1, you can train, you can run our scripts in a few minutes. And that's why I pointed this out specifically because it's a small one. But our largest data set is like rel Amazon, where it takes 1 to 2 hours to train the GNN um, on like a simple GPU, not even an 800. I'm trying to think what GPU I use for these experiments. It was like a Quadro P8000 or something. So yeah, the training the GNN part is not hard, and it's scalable up to how many rows that we have in the current data set, at least. Like scalability was not a challenge that we faced in this work, at least.
Not directly related to the question, but what's the largest scale you have worked with? And also, what kind of scale do you think like a foundation model would do?
So largest scale of what? Are
In
you
terms
asking
of
about?
the number of rows or yeah.
Yeah, so these are the largest. So 15 tables, 41 million rows, 140 columns. That would be the largest.
Okay.
So 41 million rows would mean a graph with 41 million nodes,
Right, right.
right? And then to your second question about the scale that a foundation model would need. So I've been thinking about this, and there are two different answers. So one is at the inference stage, like, so for example, if you want to do in-context learning on with your foundation model, then you might be interested in how much data can I feed into the input context of the foundation model to for it to make a prediction. And I think for that, the answer will have to be small. Like you cannot put an entire new database with millions of rows into the context. So there you can either think of fine tuning the foundation model on that new database, or if you're doing in-context learning, then there has to be a retrieval step before that where you retrieve the relevant rows, the relevant tables for the particular query that you're answering, and you only inference the foundation model on those retrieved rows and columns. And then the second part of the answer is for training the foundation model, I think we would need a lot of scale, and the scale would be more in terms of the data diversity than the number of rows in a single database, because you want your foundation model to work across different kinds of domains. or like across different databases. So if you just train it on a lot of rows from a single database, you have a model for that particular database. I don't know
Right.
if that's a foundation model.
Right. So then you get into the multitask kind of learning setting where each table may have different number of rows and you don't want to be just training on to one particular schema and so on. So that makes sense. Yeah, so happy to discuss more like offline. And so thanks so much for the presentation today. I think it was very clear. And we'll also have the recording up on the reading group website, so like people can view as well. So thanks everyone for joining the talk today, and thanks to our speaker again for the great presentation.
Thank you.
Thank you.
Thank you.
See you.
See you. Bye-bye.
Bye.